Okay. So it is my great pleasure to have Beata Zjawin today from Gdansk University, talking about her recent work about EPR correlations and quantifying EPR, the resource theory of non-classicality of common cause assemblage. So Beata now is in the group of Belen Science in Gdansk. Before she was in Perimeter Institute working with Rob Speckens, where she was telling me just a few minutes before that she got into quantum foundations there during her stay in Perimeter. And before she was working on atomic optical clocks and optics for quantum optics for astrophysics. So like a big change, but a change that is surely very rich and fruitful, because it means that she also has some background in experimental physics, which is something that is always good to have. Okay, so as for the questions, if people in the audience have questions, I would advise people to write something in the chat or raise a hand using the reactions button, and I will try to interact with Beata. Do you accept, Beata, do you accept questions during your talk, or you prefer to have them?
Yeah, of course. Feel free to interrupt me during the presentation if something is not clear. Or yeah.
Okay, so I leave I leave the spotlight to you, and okay, I will mute myself and go away. Okay, thank you very much again. Please start.
Thank you so much, Francesco, for the invitation and for the very nice introduction. And thanks everyone for coming. Let me introduce myself again quickly. My name is Beata Zjawin, and I am a PhD student at ICTQT. As Francesco mentioned, Belen Science is my supervisor here, and you can see she's also a collaborator on this work. And other collaborators include David Schmidt, who is a postdoc in our group, so he's in Gdansk right now as well, and also Matti Hoban. If you have any questions about this work, of course, feel free to interrupt me, but you have my email address here as well, so feel free to reach out to me if you have any questions. Okay. So today I'll be talking about quantifying EPR, the resource theory of non-classicality of common cause assemblages. And this work is on arXiv. So again, if you want to know more about what I'll be talking about, again, feel free to reach out to me or look at the paper. Okay, so let me start with a question. So here you can see that the title starts with quantifying EPR, but what does it really mean, and what are the scenarios that I will be talking about today? I'll be talking about steering, and the question that I'll be starting with is steering spooky action at a distance? Because it is sometimes referred to this way. So steering is a form of non-classical correlations that arise when one considers measurements performed on half of a bipartite system prepared on an entangled state. So let's try to make a figure out of this one sentence. So this is a so-called steering scenario. We have these two parties, we have Alice and Bob, and they share a system. So they share this system. And on this figure, I will use double wires to represent quantum systems, and I will use single wires to represent classical systems.
Wait a second. I think that you are not sharing the presentation. You are sharing the PowerPoint window.
Oh, really? Huh, interesting. For me, I can see it like on full screen. So you can see like the whole PowerPoint window.
Yes, I can see the whole PowerPoint.
Okay, let's try to. What if I? How about now?
If you.
Is it still the PowerPoint window? Because I just started.
Yes.
Okay. You know, maybe I'll just try to share the PDF that I send you.
Oh, okay. That would also do.
Maybe
yes.
it will be easier this way. But I don't know if I can. Maybe like this. Oh, okay. Is it better now? Can you see like on the full screen? Or can you see the like the PDF version?
I still see the PowerPoint window. Is it
Oh,
just me?
okay.
Or
So maybe let me, okay, stop sharing and I'll share again. This. Okay. Okay.
yeah, now
How
it's
about now?
changed. Now I can, yes, now I see the PDF full size, full
Full
screen.
size. Okay, great.
Okay.
Okay, thank you for letting me know.
Okay, thanks.
Okay, so I stopped here. Okay, so I was talking about what the steering scenario is. So we have two parties, Alice and Bob, and they share this bipartite system. And here you can see that I'm assuming that it's a quantum system. So it does not need to be a classical one. It can be a quantum system prepared on an entangled state. And the system is distributed to Alice and Bob. And now what Alice does is she has this measurement device that has a classical input, here denoted as X, that corresponds to a measurement setting, and a classical output, here denoted as A, that corresponds to a measurement outcome. So Alice has this black box device that takes her share of the entangled state, and she performs measurements on it. Now, when she performs this measurement that's labeled by an outcome A given a setting X, what we will see on Bob's side is a conditional quantum state that I denote as here. So you can see it's some quantum state and it's A given X. So you can see that's what's happening on Bob's side depends on Alice's measurements, setting and outcome. Now, what does it mean that we have two space-like separated parties and Bob's system depends on what Alice is doing? So this is why steering is sometimes referred to as spooky action at a distance. And this is why Schrödinger called it steering in the first place, because he said that Alice is steering Bob. So by performing measurements, she's somehow influencing the quantum system on Bob's side. And this is why it depends on A and X. But now a different perspective on the EPR scenario is the following. So we can also say that Alice just updates her knowledge of the state of Bob's system by performing a measurement on a system correlated with his. So as you can see, this is still the same picture, but the narrative here is totally different because now you're saying, okay, Alice and Bob share this system that is correlated, and this is why where Alice performs some measurements on it, she's updating her knowledge about what's happening on Bob's side. And this is still consistent with the view that Bob's quantum system will depend on Alice's measurement setting and measurement outcome. But in this narrative, we don't really say that Alice is steering Bob. She's not influencing Bob in any way. She's just updating her knowledge by performing these measurements. And it's all because they have the system that was initially correlated before it was distributed to Alice and Bob. And actually, this is the perspective that Einstein, Podolsky, and Rosen, so this is what EPR stands for, endorsed themselves. So what they said is that there's no spooky action at a distance here. So there's no causal influence on Bob's system, or in other words, there is no steering here. It's just, this updating of knowledge due to this shared system, which I will later refer to as a common cause of Alice and Bob. Okay, so is steering spooky action at a distance? No, we don't really have to view this way. And in this presentation, I will endorse the viewpoint of EPR of Einstein, Podolsky, and Rosen. And I will, because of this, I'll find the word steering itself to be really not suitable for this situation. And I'll just refer to this kind of scenario as an EPR scenario. So when I say an EPR scenario, this is what I have in mind. Okay,
there is a question from the audience, from Arthur, who asks, maybe you can read it also in the chat. Is it really that Bob's system depends on the measurement choice and outcome, or rather that Alice's knowledge of Bob's system is given by the state rho?
Yeah, this is exactly the second one. So what's really happening is like Alice, by performing a measurement and getting an outcome, on Bob's side, we'll just have an assemble of assembles of these conditional states. So depending on A and X, Alice's knowledge will be just, taking this one assemble from this assemble of like all possible assembles of quantum states for all possible A's and X's. So yeah.
So in particular, the form of this diagram is in some sense from Alice's perspective. Writing row A/X means that I'm thinking of this diagram from Alice's point of view. But Bob's, like from Bob's point of view, Bob has no idea what Alice is doing, no idea what the measurement is. So Bob's density matrix a priori shouldn't necessarily depend on X, correct?
So what Bob has, so for example, if you trace out Alice, you'll just get like some density matrix on Bob's side. Okay, and it will be like equivalent to what happens if you like sum over all A. So you just trace out Alice. Yeah, and then it will be independent, of course. Yeah, but like for one particular measurement setting an outcome, you can say, as you said, that like from this perspective, Alice is updating her knowledge about Bob. But yeah, once you trace out, it will be independent.
Okay, thank you.
Okay, so I'll refer to these scenarios as EPR scenarios. And just to recap this like more foundational introduction, because as you can see for both cases, we have the same drawing here. And a lot of people do interpret that it's spooky action at a distance. And it doesn't change the scenario itself, but then it has big implications, for example, on the resource theory of EPR scenarios. So this is what you will see throughout my presentation. But just to recap this, what Schrödinger initially took this scenario to be was motivated by the fact that he took quantum state to be a physical property of a system. And he called this scenario a steering scenario and assumed that like there must be some superluminal causal influence from Alice to Bob, because her measurements that are local to her laboratory somehow influence what's going on in Bob's laboratory as well. So this is, of course, not the words that Schrödinger used, but in the modern language, we could say that he had a psiontic view, which means that he took distinct quantum states to describe distinct physical states of the world. And this is not the approach that I'll take in this presentation. The approach that I'll take endorses the EPR perspective, which is that quantum state is a representation of one's information about the system. So here you have no causal influence from Alice to Bob, and Alice just learns about the true state of Bob's system by performing these measurements. And again, in modern language, we could say that this is the epistemic view, that quantum states represent states of knowledge about the world and not physical states of the world. Okay, so all of that said, let me move to the resource theory of EPR scenarios. So first, let's formalize what we mean by the EPR scenario. Still the same picture. And it's the defining feature of it are the common cause causal structure. So again, I'll refer to this shared system as a common cause that's shared between Alice and Bob. And the most important thing here is that there is no influence from Alice to Bob. So there's like no communication tunnel here, and all that we have is this common cause. And the other defining feature is that the types of system the parties have access to. So on Alice's side is just a classical input and a classical output. And on Bob's side, you can see that apart from this shared state, he does not have any inputs, and his output is just the quantum state. So here we have classical input to classical output, and here we have a trivial input, so no input at all, to a quantum output. Okay, and I'll be talking about quantum assemblages here. So quantum assemblages are the relevant objects in the EPR scenario, and they're defined like this. So this is what I'll call an assemblage, and it's this collection of these small sigmas for every I and X, where sigma is defined like this. So it contains information about both what's happening on Alice's side. So this is a probability distribution that Alice will observe an outcome A when she has a setting X. And this is the conditional state on Bob's side. Okay, so this object is what I'll refer to as quantum assemblage. And now one comment that I want to make is that in this resource theory of EPR scenarios, quantum assemblages will be the resources. And there are some different ways in which you can tackle it, and I just want to comment on that. So for example, here you can see that I'm assuming that Alice and Bob share a quantum system. And what you could do is you could construct a resource theory of EPR scenarios where the resources will be the quantum systems that Alice and Bob share. So instead of looking at assemblages as object, in and of itself as a whole thing, you could just look at the quantum state and ask, okay, what is the resourcefulness of, like, in an EPR scenario given a particular quantum state? So of course you can do that, and this is how EPR scenarios were originally studied. So they're just used as sort of means for entanglement certification. But in recent years, people actually started to look at EPR scenarios from this perspective of assemblages, and this is what I'll do in this presentation. Okay, so why do we want to construct a resource theory? Resource theories allow one to formally quantify physical resources. So again, in our theory, the physical resources are the assemblages, and what we want to quantify is the non-classicality of these assemblages. Now, the structure of a resource theory is completely determined by the set of free operations. Free operations are the operations that cannot create a resourceful object. And in this case, a resourceful object is one that is a non-classical object. So it's a non-classical assemblage. So in other words, the classical or the free objects in our theory will be the classical assemblages. And now our approach just follows from the recent developments of resource theories for studying non-classicality of common cause processes, wherein the free operations are local operations and shared randomness. So I emphasized before that what we have here is a common cause structure, and taking LOSR operations, so local operations and shared randomness, to be free operations in such a structure is a pretty general thing to do. And some examples of a different common cause processes, different than EPR scenarios. For example, entanglement is an example of such a common cause process. So this is an entanglement scenario where you just have an entangled state that's distributed to Alice and to Bob. And in this paper here, you can find the resource theory of LOSR entanglement, where LOSR are the free operations. And a different example of a common cause process is a Bell scenario. So what you have here is you have this box that's a common cause to Alice and Bob, and both Alice and Bob perform measurements on this system. Now, another comment here is that you will see a difference that here I have double lines. So this is just an entangled state, but in a Bell scenario, instead of a double line, I have this thick line here. So what does it mean? It actually means that it can be a post-quantum common cause. So in entanglement scenarios and in EPR scenarios, we can actually assume without loss of generality that the shared common cause is quantum. While in the Bell scenario, it's possible that this is post-quantum. And for example, the correlations that Alice and Bob generate are PR box correlations. So I'll just focus on quantum theory in this talk. But if you're wondering why this difference here, then it just represents post-quantum resources. Okay, if you want to know more about common cause processes, then there's also this I have here, which is a type-independent resource theory of common cause processes under LOSR. But I'm guessing that Francesco's group will be familiar with that. Okay, so an EPR scenario or assemblages are basically just another instance of a very general construction of common cause processes. And I'll just focus on this one instance in this presentation. Okay, so our free operations are local operations and shared randomness. And now what does it mean for the free objects? So once again, this was our general assemblage where we have a quantum common cause Now, the free assemblage is one when we have a classical common cause. So shared randomness just means the same thing as classical common cause, which means that this box here is classical, and it's a classical variable here denoted as lambda that is distributed to Alice and Bob. Now we also have local operations. So Alice can perform any local operations. Here she performs this, not measurements, but here she will just have some probability distribution of getting the outcome A given her input X and the value of the shared variable lambda. And on Bob's side, what's happening is he gets this value of the shared randomness, and he generates a quantum state depending on this lambda. So this is exactly what's written here. This is how we can decompose a free assemblage. So just for each value of lambda, Alice gets this probability distribution, and through this she can infer about Bob's states. So again, you can see that in this expression we don't have p of lambda, and it's because it's hidden here. So because this is an element of the assemblage, this is really p of lambda times rho lambda. So this is not normalized. Okay, so these are our free assemblages. Okay, and there are different approaches that one can take. For example, a few years ago, there is a paper that constructs a resource theory of steering under S one-way LOCC, which stands for stochastic one-way local operations and classical communication. And of course, there are valid approaches as well. The main constraint in the resource theory is that the free operations cannot create a resourceful objects, and LOSR operations cannot create an assemblage that is not free. And the same stands for this as one-way LOCC operations. But just the motivation for this resource theory and for our resource theory is very different, and I will compare them a little bit later. Okay, so how does the LOSR operations look like? What you have on this figure here is in black, we just have the same old assemblage, and in green, we have the LOSR operation. Okay, so let's start with the shared randomness part. We have this shared randomness that can be distributed to Alice and Bob. It's represented by this box here. And now on Alice's side, we have the local operations, which is the local classical pre-processing of her input X. So effectively, Alice will have some new input X prime. And then she also has a classical post-processing of her output A. And notice that both of these can depend on the value of the shared randomness. And now what we have on Bob's side is he can also perform local operations, but now because he has a quantum system, this box corresponds to a general CPTP map that he can apply to his original system to transform it to a new one. And this CPTP map can also depend on lambda, so it can also depend on the value of the shared randomness. And effectively, what this operation does is, at first we just had this assemblage here in black, and now we just have some new one that depends on the primed values after pre and post processings. So this is the most general LOSR operation that one can perform on an assemblage. Okay, so now that we specified what are the free operations that we can apply to assemblages, we can ask what are the properties of the preorder. So how we can transform between different assemblages using our free operations. So using transformations of this form. Okay, more general, one assemblage is said to be more non-classical than another if it can be freely converted to the latter. Because of course, if we have two assemblages, assemblage 1 and assemblage 2, and assemblage 1 is useful for some task, but then assemblage 2 can be converted to assemblage 1, then the second assemblage will be as useful as the first one, right? Because we can always apply free operations to transform between different assemblages. So if you are interested in relative non-classicality of assemblages, we want to see what conversions between assemblages are possible under LOSR and what are not possible. So again, we will be looking at this LOSR transformation. And what we showed in the paper is that assemblage conversion under LOSR can be tested using a single instance of a semi-definite program. So this is very useful because it's very tractable. If I have two assemblages, I just plug them into the semi-definite program and I get an answer about which one is, like which conversions are possible. So ultimately, which assemblages, like the relative non-classicality of two assemblages. And this is the program. So maybe let me go over it quickly. What we are given in the program are two assemblages. So this one here, the primed one. And the question that I'm asking is whether this assemblage can be converted into this assemblage. Now, what we also input are this probabilistic, deterministic probability distributions, and they correspond to Alice's pre-processing and post-processing. So they correspond to this box and to this box. Okay, so I have this deterministic probability distributions, and now what I'm looking for is, maybe let's go from the bottom up. We want to know whether this assemblage can be decomposed in this way. And it basically means that all of this represents an LOSR transformation on our original assemblage, okay? So we have the deterministic probability distributions here. So this corresponds to Alice's pre-processing and post-processing. And the part that we have here corresponds to Bob's post-processing. So let me remind you that Bob's post-processing was just a CPTP map. And what you can see here is the this W is a toy form of the CPTP map. Okay, so what we are looking for in our SDP is we're looking for this W. So we're ultimately looking for this quantum post-processing on Bob's side that enables this LOSR transformation. And the conditions that we have here are just the conditions that this must be a CPTP map that Bob is performing. Okay, so as you can see, it's pretty simple SDP, and given two assemblages, I can just run it and I can see what is the relative non-classicality. Artur, do you have a question? Because I see that you're...
Oh, great. I wasn't sure if you can see that or... okay, yeah,
Yeah,
so
I can.
you have, so I'm a little bit confused. I was assuming that the objects in your category are these assemblages. So they're given by the sigmas. And then a morphism is one of the form that's actually given by these Ds, right?
So the Ds, okay, let's see if this answers your questions. So in general, when we just write down the LOSR transformation, these won't be deterministic probability distributions. So like in a general transformation, we'll just have a probability distribution and we'll have the CPTP map. But like because of the Fine's theorem, and there's some later work on it, we can actually rewrite it in a way that these are deterministic probability distributions. And because we'll always be working with like finite cardinalities A and X, this is something that we can just list. And this is why it's also like an input in our program. But in general, like the most general form that when you write down the LOSR transformation, this won't be deterministic probability distributions.
I see. So are you looking therefore at a subclass of morphisms?
Yeah.
Of all?
Yeah.
Okay, and then you're solving, and then you're trying to see if you can go from sigma to sigma prime using this subclass.
Yes, exactly.
Okay, great. Thank you.
Okay, so this is the SDP, and we use it to check possible conversions between different assemblages, and here are the results. So we found an infinite family of incomparable resources, incomparable meaning that none of them can be converted into any other. So the family that we looked at is specified here. So again, let's look from the bottom maybe. So these are the measurements that Alice is performing. So you can see we have two possible x's. So x is either equal to 0 or it's equal to 1. And depending on the value of x, these are the measurements that Alice is performing. And she's performing them on her share of the state. So this is the state that Alice and Bob originally share. And it's an infinite family of assemblages because we can vary over different values of theta. And this is the expression for an individual element of an assemblage for a given A and given X. So as you can see, Alice is performing this measurement that's specified at the bottom. Bob is doing nothing. This is the state that they share. And then we trace out Alice to get the assemblage. Okay, so we did run the SDP. We did it in MATLAB using CVX for different values of theta. And we kind of got a hint that all of this will be incomparable. So like for different values of theta, and none of like individual assemblage can be converted into a different one with a different value of theta. But we are also able to confirm this, this result analytically. So what we did also is we, using EPR monotons, so we constructed an infinite family of EPR monotons that certify this result. So they certify that this is an infinite family of incomparable resources. And maybe let me not go into the details here, but like for those of you that know a little bit about resource theories, we just constructed this family of monotons. And basically what needed to be shown is that if we take two different assemblages for different values of theta, theta1 and theta2, we can always find a monoton that will act in this way. Okay, so this implies that theta2 cannot be converted to theta1 under LOSR. And at the same time, we needed to find a different monoton that will act in the opposite direction. So it will imply that this conversion is impossible in the opposite direction. So we were able to do this by constructing some EPR inequalities from Bell inequalities. So we just took tilted Bell inequalities, constructed EPR inequalities from them. And from these EPR inequalities, we were able to construct these monotons for every value of theta, basically. So we are able to certify this for every value of theta. Okay. And then one more thing that we looked at is a family of assemblages that was indexed by 2 parameters. So before we only had this one parameter theta here that we varied over. Now we have another one, T. So this assemblage is just what we had before. Okay, so it's just this one. But now what we are doing is we're additionally mixing it with noise. So the assemblage that we're looking at right now is indexed by this parameter theta and also parameter P. And it's defined like this. So with some probability P, we have this assemblage, and with probability 1 minus P, we just mix it with noise, basically. And we look at this family of assemblages where P, we just varied it from 0 to 1. And you can see the results on this plot. So here, each dot corresponds to one assemblage. So for example, this dot is an assemblage where theta is equal to pi over 4 and P is equal to 1. So here we didn't mix with noise at all, and Alice and Bob shared a so-called maximally entangled state. But for example, this dot here is where we mixed with noise, and like P is equal to 0.9 and theta was equal to pi over 12. So again, each dot represents one assemblage. And now the gray, there's only one gray dot, and this is a free assemblage. So this one can actually be generated with LOSR operations. This is not a non-classical assemblage. And the gray dots, the gray arrows, sorry, correspond to trivial conversions. Because if you have an assemblage and you mix it with noise, well, you can always transform this one to this one, where this one is mixed with noise, just with LOSR operations. So these are the trivial conversions. Okay, so now that we understand what's on the plot, the arrows just correspond to possible conversions that we are able to find using our SDP. And again, it was done in MATLAB using CVX. So the different colors here, they don't really matter. They just, it's just so the picture is more visible. But as you can see, well, this result is like, it's not very intuitive, right? You can see that the conversions, like it's not symmetrical. And yeah, I don't want to say that you cannot make a lot of sense out of it, but as you can see, it's like not symmetrical. And yeah. One thing that's interesting is that when we mix with noise, it's already possible to have conversions like within this family. So the result that I had before is that with this family, all assemblages are incomparable. So we have no errors here or here. But when we mix with noise, it's already possible. So for example, this assemblage can be converted to this one. Okay. So as I promised, I will compare it to the previous resource theory of EPR scenarios. So it was introduced in this paper by Rodrigo Galileo and Leonardo Aulita, resource theory of steering. And the three operations there were stochastic local operations and one-way classical communication from Bob to Alice. And this is what you can see in green here. So again, in black, it's the same assemblage that we had. And now what we have is that Bob performs this post-processing, but now except like he has this quantum output like he had in the LOSR case, but he also has this classical variable that he can now communicate to Alice. And as you can see, Alice's pre-processing now depends on the message that she received from Bob. So this is the part of one-way LOCC that's here. And then Alice just has this pre-processing and post-processing. So, oh, and they're stochastic, so they can just like happen with some probability, these operations. So quite obviously, it's a different resource theory from ours. As I said, there are both like formally proper resource theories, both as one-way LOCC and LOSR are formally proper sets of free operations for assemblages. But there are some differences between the resource theories. And the first one is that there are different pre-orders, which is kind of to expect too, because the free operations are different. So now we are looking at conversions under a different set of operations, right? And in particular, this is the plot that we had for LOSR. And in particular, here the assemblages were incomparable, but for S one-way LOCC, the singlet assemblage, so this one here, is actually above others in the family. So it's possible to convert this assemblage to other ones with different theta values. And in our paper, we're able to provide possible conversions with a stochastic LOSR and one-way LOCC. Like we are able to provide specific protocols that actually transform the singlet assemblage to assemblages with different values of theta. Okay, so that was a very technical difference between the resource theories. There are also some conceptual advantages of our approach over the S one-way LOCC approach. For example, our approach has a very clear physical motivation. So as I said, the set of LOSR operations is motivated by the fact that an EPR scenario is a common cost scenario. While here, the motivation was that assemblages are known to be useful for one-sided device-independent quantum key distribution. And the motivation of authors in this work was to get the most general set of free operations such that the protocols for one-sided device-independent quantum key distributions would be safe. And this was the motivation. So it was motivated by this one particular experiment that assemblages are known to be useful for, which is of course a valid motivation, but ours is just from the conceptual point of view, ours is more general, I would say. And because of this, we get this unification of every type of non-classical correlation in Bell-like scenarios. So, yes, Arthur?
Yeah, so you just said this and I was wondering, because you're saying that your setup is more general, does that mean that your class of morphisms is a strict subset, or rather
Yes.
superset? Yeah, subset?
Like LOSR is a subset of LOCC.
Okay, great, but the assemblages are exactly the same. So your objects are exactly the same. Okay, great,
yes.
Thank you.
Yes, and we get this unification of common cost resources. So because we can take LOSR operations to be free operations in a resource theory of EPR scenarios and in a resource theory of entanglement and in a resource theory of Bell scenarios, And the LOSR can be taken, to be free operations in a resource theory of any common cause processes. We could disconstruct, and this is what was done in this paper, basically a very general resource theory of common cause resources. And now, why is this useful? Because, for example, you could study conversions between different types of resources, right? While when you take the LOCC approach, then when, in entanglement, we talk about LOCC, but in EPR scenarios, they talk about one-way LOCC. So it's maybe not that clear how to compare different kind of resources. And there are also some technical advantages of the LOSR approach. So it's simpler to characterize and study. The SDP that I showed you is one example. As far as I'm concerned, there's no tractable way of checking conversions under as one-way LOCC for assemblages. And another advantage is that under LOSR is very easy to generalize everything that I just said to different scenarios, to different EPR scenarios. For example, multipartite EPR scenarios. So this is a scenario where we have more Alices and one Bob. We could also have more Bobs, but this is the one that I'll focus on. And we actually did it in our work, and I'll talk about it a little in a second. But there are also other generalizations that you can do. For example, to Bob with input EPR scenario. So a Bob with input EPR scenario is one where you have the EPR scenario, but the Bob now has a classical input as well. And it was shown that, for example, in this case, you can have post-quantum assemblages, which you cannot have in the general EPR scenario that I was talking about right now. So you can even talk about post-quantumness within this framework of LOSR. And you could also generalize it to channel EPR scenarios, where channel EPR scenario is the scenario introduced by Marco Piani that he referred to as channel steering, and is basically when Bob has a quantum input and a quantum output. Okay, so let me talk a little bit about the multipartite EPR scenarios. But we are also working on the Bob with input case and channel case, so post-quantum cases. And I will not talk about it here, but if you have any questions, just let me know. Okay, so multipartite scenarios. So the scenario that you can see in here, we basically have two Alices and one Bob. So this is Alice 1, this is Alice 2, and this is Bob. And as you can see in green is the LOSR operation. And it's pretty straightforward. It's just a direct generalization of what we had in the bipartite case, except that, the shared randomness is now distributed between free parties and not free parties. So we have the shared randomness distributed to Bob, to Alice 2, and to Alice 1. And on top of that, each party performs local operations. So Alice 1 has her pre-processing and post-processing. Alice 2 has the pre-processing and post-processing, and Bob has the quantum post-processing, just like he had in the bipartite scenario. So in this case, we are able to show that assemblage conversion can be also tested using a single instance of a semi-definite program. And we are also able to find a family of incomparable resources. So this is pretty much all in analogy to the bipartite scenario. So let me not focus on it here, but I do have one thing about multipartite scenarios in particular that I want to discuss. And this is the definition of a free multipartite assemblage. And by free, people sometimes say unsteerable in the literature, but I basically mean a classical assemblage. Okay, so the most general definition that you will find in the literature of a free or unsteerable assemblage is this one. So this is assemblage. Again, we have like two Alices here, Alice 1, Alice 2, and it's just, the sum over lambda, so the sum over the shared randomness in our case, or sometimes people refer to it as hidden variable. We have this probability distribution of Alice 1 and Alice 2, the outcomes given their inputs, and we have Bob's system. And now, what could be a problem with this more general definition is that there are no restrictions on this probability distribution. So of course, this assemblage must be non-signaling, but in this definition, it's possible that some individual probability distributions will be signaling between the Alices, and it's okay as long as the signaling will average out when we sum over lambda. And some people see it as a problem. I do, for example, because if the assemblage is non-signaling, it makes sense to imply the non-signaling condition between Alice 1 and Alice 2 from the very beginning. And one problem that occurs when you take this general definition of a free assemblage, and I will just comment on it shortly, is something called exposure of steering. So if you take this definition to be a free assemblage, like this equation to define a free assemblage, then it's possible to have steering exposure, which means that you have a multipartite assemblage that is free. And from this free assemblage, you can create an assemblage on a less number of parties that will not be free. So for example, you could have free parties and you could have a free assemblage that would be free according to this definition. But then from this, you could make a bipartite assemblage that is not free. And this phenomena is referred to as an exposure of steering. And it was also studied in the literature. And it's basically because of the fact that you're allowing signaling probability distributions here. Okay, so in our approach, this problem does not occur at all. Because if you look at this picture, you can see that for Alice 1, her pre and post processing only depend on the value of lambda, of the shared randomness. And for Alice 2, it is also the case. So this probability distribution for LOSR approach will factorize. So there's no possibility that will be signaling between the Alices, and therefore, like a probably in our resource theory, you will not find phenomena such as exposure of string. Okay, so that's all that I wanted to say today. So let me just make some final remarks and to emphasize the most important points of the presentation. So I introduced a resource theory of common cause assemblages for both bipartite and multipartite scenarios. And this resource theory was motivated by a very, very clear causal interpretation of an EPR scenario. So as I said at the very beginning, the EPR, Einstein, Pulowski, and Rosen themselves thought of this scenario as this, correlation through a common cause and not as causation from Alice to Bob. So this is also why I didn't refer to this scenario as steering, but simply as an EPR scenario. And now, because of this view, we have a unified notion of common cause resources. So EPR scenarios, Bell entanglement, and this unified notion is this resource theory where the three operations are local operations and shared randomness. And now for the EPR scenarios, testing convergence is numerically tractable. So we had this SDP that you can test assemblage conversion with a single instant of the semi-definite program. And we also had some interesting properties of the preorder. So for example, we had this infinite family of incomparable assemblages where the infinite family was indexed by this parameter theta. And finally, for the multipartite case, we had a well-motivated definition of a free multipartite assemblage. So yeah, thank you for your attention. And again, if you have any questions, you can ask them now, or you can just email me. And I encourage you to look at our paper. Thank you.
Thank you very much, Beata. Very nice talk. I really enjoyed your presentation. So I would first give priority to the audience. If anyone has a question for Beata, Minagawa-san and Takagi-san. Okay, so let's start from whom? From Shintaro. Okay, would you like to ask it directly?
Yes, in the closely related paper whose title is Quantifying EPR, in my memory is correct, the assemblage convertibility condition was given by linear program, but in your work, it is SDP. So why the difference? Why does the difference occur?
So in our case, as you said, thank you for the question. For the EPR scenarios, it's an SDP. And in the Bell quantified paper, they're talking about Bell scenarios, and it's actually a linear program. And if you would look at this paper for entanglement under LOSR, it's actually a hierarchy of SDPs. So you can see that, like I don't have a very technical answer to your question, but you can see that as long as you have this classical inputs and outputs here, you'll get the linear program. And once you have a quantumness on Alice's side, you'll get an SDP.
Okay, I understand. Thank you very much.
Thank you.
Ryuji, would you like to ask your question directly?
Yeah, sure. Thank you very much for your very nice talk. And I have two questions. And the first question is related to Shintaro's question, I guess. So you looked at the infinite number of assemblages that cannot be converted to each other. So did you also take a look at this question in a Bell scenario? And do you know if there is such an infinite number of, I guess, in this case, probability distribution, conditional probability distribution that cannot be converted to each other?
Yeah, so I think it's the same in all scenarios, and it's all inherent to the entanglement scenario. So in LOSR entanglement, all these theta states are incomparable. So in LOCC, we do have this relation that like the lower you go with theta, it's possible to convert one state into another, right? With this theta states. Now for LOSR, this is already impossible. So under LOSR, here we already have an incomparable family of states. And for example, our result for assemblages relies on this fact. So it's all kind of inherent to the entanglement scenario. And it's the same in the Bell scenario where two parties share this theta state and then they just perform measurements.
I see, sure. So the second question, I guess, is related to the first thing that you mentioned, the entanglement theory and so forth, where in entanglement theory, if you go to the asymptotic limit, then the situation becomes a bit different, and you can actually characterize the distillation or even state transformations for pure state, let's say pure state transformations in terms of relative entropy measure. Whereas one-shot transformation is characterized by the measurization, which gives you some incomparable resources. So does your technique allow to investigate the asymptotic transformations and possibly the optimal distillation processes for the assemblages transformations?
Yeah, thank you for this question. I don't have an answer to it. As far as I'm concerned, there's no research about like this sort of stuff under LOSR. But yeah, I think this is very interesting. And I don't know if Bartek is still here, but he also asked me about this, like entanglement distillation under LOSR. And I thought about it a little bit, and it's definitely more complicated than under LOCC just because of this like incompatibilities and stuff. But I think it's a very interesting question, but unfortunately I don't have a very precise answer to it.
So I guess for the case of entanglement, if you look at the general mixed states, then the problem is already very hard. So I wonder if there is a nice simplification, like concentrating on the pure states. Then what is there like analogous way of thinking about this, sort of imposing some kind of purity and stuff in this assemblages business?
I don't know, to be honest. Like I think I don't know if there's any research on assemblage distillation. Maybe someone in the audience does, like even under one-way LOCC. I'm not sure.
I mean, there is one work I'm aware of, which is to discuss the achievability result. I guess like using the other framework that you mentioned, the one-way LOCC type thing, then just show that it is possible to, very simple case, it is possible to synthesize the singlet assemblages from some very restricted class of the assemblage. Just I was wondering, I guess with Shintaro, if that's optimal or not. So that led to this
Okay.
problem. Yeah.
Okay. Well, then I don't know, but like one thing that I would say is the first thing to do under LOSR would be still to look at like entanglement, and then maybe try to get some like intuitions and go to assemblages.
Right. Yeah. Thank you. Thank you very much.
Thank you.
Okay, any other questions from the audience? If not, I would have one question myself. So as you know, in my paper, in 2012 paper, the all entangled states are non-local, which is a little bit, the grandfather of these new papers that use the LOSR formalism for interconversion of bipartite or multipartite resources. I characterize interconvertibility by LOSR in terms not of a single instance of a semidefinite program, but in terms of an infinite but compact family of games, kind of guessing games. So I came up with a kind of situation where Alice and Bob has to play a game very similar to the usual non-locality scenario that is quantified and characterized in terms of bell games, non-local games. I came up with another formalism, but that can still be interpreted as a game. So it has a disadvantage with respect to the STP formulation that, of course, you need an infinite set of monotones to characterize the interconvertibility. But on the other hand, you have a more grip on the resource that is at stake in your theory, right? Which is something instead that gets lost if you consider only the SDP scenario, because you have both things at the same time. So do you have have you thought about constructing, because I think it should be possible to do that, have you thought about constructing a complete set of monotones for your theory? Like monotones that are sufficient and necessary and sufficient for interconvertibility.
Yeah, so we thought about it, but we didn't find a complete set. So I know that like in your case, or like, for example, for the Bell scenarios, they're able to find a complete set, but we didn't. But I think it's like, I don't think it's a technical limitation. I think it's that we are not able to do it, but in principle, I'm guessing that it should be possible. It was maybe just not very straightforward.
Okay. Okay. Yeah, maybe we can discuss about it later, because I think that the two formulations are, in a sense, how to say, they are dual to each other, right? So the SDP just tells you that if you want, you can just plug these two objects in an SD semi-definite program, and this spits out whether there exists or not transformation. On the other side, you have a more abstract viewpoint, but somehow it tells you this scenario in which one can win more than the other. So you get more intuition about really what's the resource at stake there. Okay, that was just a comment, but it's interesting. We can keep discussing about it.
Yeah, definitely. Yeah, thank you for this question.
Other questions? Okay, so if not, I would thank again Beata very much for accepting to give a talk, and for sharing with us her insight on this very interesting problem. And I wish you, Beata, all the best for your PhD, because you are still PhD student, right?
Yeah, yes.
Okay. Okay, so thank you very much.
Thank you.
And thanks to all participants again.
Yeah, thank you again for the invitation, and thank you everyone for coming.
Okay. I will stop recording.